Okay, we're graphing growth and decay functions. So first thing we're going to do is identify the parent graph, and the parent graph is always the base to the x. So for this one, it's going to be y equals 1/2 to the x. Because the base is 1/2 and 1/2 is less than 1, we know this is going to be decay. For the table, before we can start the table, and we have -2, -1, 0, 1, 2, and then we're going to plug it into the parent graph. So this is going to be 1/4, 1/2, 1, 2, 4. So again, I'm getting these by going 1/2 to the -2. That's what equals 4. So I'm plugging each of those in. The next thing I'm going to do is look at my transformations, and I have a vertical stretch. Remember, we have to write vertical stretch, not VC, by 4. And then we're going to go left 3, and we're going to go down 2. So what we were saying earlier, normally we do all of this in the table, but because we have fractions, it's actually faster to just do reflections and stretches or compressions in the table. And then from there, we'll just move it left 3 and down 2. So we'll do the shifts on the graph, but the stretches and compressions we will be doing on the table. So we have stretch by 4, so we're going to multiply all of our y values by 4. So that gives us our new points are going to be 16, our new y coordinates. So when we do that math, we get those values. So then we're going to plot those values. So -2, 16 is like way up here. And then we have -1, 8, 0, 4, 1, 2, and 2, 1. And right now, because we haven't moved up or down at all, our asymptote is right there. So what we're going to do now is do the last part down here, which is left 3, down 2. So you're going to take each point and go left 3 and down 2. Left 3 and down 2. Left 3, down 2, left 3, down 2. You don't have to do that top point. Just make sure when you draw it, it'll be in there. So now we are going to put our asymptote. We know our asymptote is always going to coast along the shift, the up or down shift. So since that's at -2, our asymptote is going to be right here at y equals -2. And then we have our graph. We know it's coming down steep. It's not a slow process until it starts to coast along that asymptote. Domain, we always know, is all real numbers for exponential functions. It's always the range because of that asymptote. So we know the asymptote is at 2, and because our graph is above it and can't touch it, we're just going to be greater than 2. Okay, next one. We have another one. Our parent graph, like we said before in the previous problem, is always your base to the x. So this is going to be y equals 2 to the x. And because that base is a 2, that's going to be growth because it's bigger than 1. So we start by making our table for that. We're picking the standard 5x values and plugging them into the parent equation, which is 2 to the x, so we get those values. Then we're going to identify our transformations. So we have the reflect over the x-axis. Make sure you put over x-axis. And then we also have the shift of up 5. It's up 5 because it's not in the exponent with the x. So if it said x and +5 and the +5 was tiny like the exponent, then that would be a horizontal transformation. Okay, so we always take care of reflections and stretches or compressions in the table. So we're just going to multiply all these by -1. And then we're going to do the math on that. So that's -1/4, -1/2, -1, -2, and -4. And then from there, we're going to plot those points on our graph. So -2, -1/4, -1, -1/2, 0, -1, 1, -2, and 2, -4. So this is a reflected growth graph, and our asymptote right now is at y equals 0, but we still haven't done that last transformation, which is up 5. So we're going to move all these points up 5. So 1, 2, 3, 4, 5. And then we have 5, and then 5, up 5, and then up 5. So when we move that up 5, it moves our asymptote up 5, and we've also made the connection over and over again that vertical shift is always the value of our asymptote. And since it's a vertical shift, that's why it's y equals also horizontal asymptotes are y equals. So this is y equals 5. And then we are going to make sure we draw this whole graph. Domain x such that x is an element of the reals. And then the range, again, y such that y, and it always has to do with that horizontal asymptote, but this time we're below. And again, with exponentials, you don't touch that asymptote, so we have to take off the equal to sign that we've used in the past. Last one in this row, we have 3e to the x minus 1. So again, our parent graph is e to the x. So y equals e to the x. And then because e is about 2.71 and 2.71 is bigger than 1, that's going to be growth. And then we make our table. And we know this is 2.7, 1, 7.4, 0.4, and 0.1. So if you don't have those values memorized for the free response portion, you're going to want to get those memorized, okay? Because those will not be given to you. Okay, let's see, transformations. So the ones that we're going to take care of on the table are the vertical stretch by 3. And then the one we're going to do on the graph is just going to be right 1. And again, the reason it's right 1 is because it is up here in the exponent. If it was down 1, it would have been like written like that. So it's not down 1, it's going to be right 1. Let's see. Okay, let's take care of that vertical shift. So you are going to have to sometimes multiply some decimals by hand. So we'll make it easy though. 0.3, 1.2, 3, 2.7 times 3. What's 2 times 3 is 6. Is that 8.1? I'm going to check it in my calculator so I don't tell you wrong. Even though I wouldn't be able to. Yeah, that's good. And then 7 times 3 is 21, and 4 times 3 is 12. 21, 22.3, or 22.2. Whoa. That's a lot of 2's. Yeah. Okay, so those are our values. So we're going to plot the ones with just the stretch first. So that's going to be -2.3, and then -1 is going to be at 1.2. And then we have, I'm going to cross these out so I don't get confused by those, 0, 3. And then 1, 8.1. And this other 22.2 is way too big to be on our graph, but we're just going to know that the graph is going to come from a very steep place. Currently, the asymptote is at y equals 0, right? And we're going to move everything right 1 now. So everything just moves over to the right a little bit. And then we have our asymptote. When we move right or left, our asymptote stays in place. So the asymptote is going to be at y equals 0. We also know it's going to be at 0 because we don't have anything, any shift up or down in the equation. So it would be equivalent to writing +0. That would be the invisible math. So we know it's 0. Domain x such that x is an element of the reals, and the range y such that y, and is it above or below the horizontal? It's above, so it's going to be greater than. Alrighty, so now we're moving on to D, which is more graphing. Again, it's with E. So let's figure out, again, parent graph is going to be e to the x. E to the x is always growth because e to the first power is 2.71, dun dun dun. In case you don't remember that, it's like pi. So because 2.71 is bigger than 1, it's going to be growth. Our table for that, again, this is the one that you have to memorize. So we got 0.1, 0.41, 2.7, and 7.4. Okay, transformations, we have reflect over the x-axis. And then we have a vertical compression by 1/2. And then the last thing we're going to do after we've graphed it, just because we don't want to have to add a bunch of fractions, is move it up 3. So in order to figure out these, we are going to multiply everything by -1/2. That's the same thing as changing its sign and cutting it in half. So it's not like you have to do this elaborate fraction decimal math problem. All you have to do is cut it in half and make it negative, okay, or make it its opposite sign. So for this one right here, this is going to be -1/2, or if you want, you can just make it, it's going to be -0.05 because it's already 0.1, and then we're going to cut that in half and then make it negative. So 0.4 cut in half is going to be -0.2. The half of 1 is going to be -0.5. Half of 2.7, half of 2.6 is 1.3, so it's like 1.35, so -1.35. And then half of 7 is 3.5, and half of 0.4 is 0.2, so it's going to be -3.7. Okay? So then we're going to plot those points on the graph. This one is so tiny that if you don't get it on there, it's okay. You know it's going to coast along the asymptote. So we have -1.2. I don't want to cross off -1, -0.2, because you always want to have one positive, 0, and one negative at a very minimum. The more you can get on there, the better. When it's at 0, it's at -0.5. At 1, it's at 1.35, and then at 2, the only problem is these are all negative, and I have not been graphing them negative, but that's okay. Okay, so the first one is going to be at -1, -0.2, then we have 0, -0.5, then we have 1, -1.35, and 2, -3.7. So that's the reflection and the vertical compression. And then again, our asymptote starts at 0 for all these graphs, but now we're going to move all these points up 3. So 1, 2, 3, 1, 2, 3, 1, 1, 2, 3, 1, 2, 3. And when we do that, the asymptote moves up, so then we get all the way down. Like that is what our graph looks like. The equation of the asymptote is y = 3. The domain is x such that x is an element of the reals, and the range is y such that y, and then it's at 3. But again, because this graph is now below this line, we're going to change this to less than. Okay, that's it for the graphs right now. Now we're going into all those word problems. So make sure you highlight key words and make sure you have a good understanding of this situation. So a cell phone valued at $800 depreciates. So depreciate is going to lead us to decay. And then $800 is our initial amount. Okay, the rate is 16.2% per year, and we also know that we need to convert that to a decimal, so it's 0.162. write a function that models the value of the cell phone. So we're going to start with our parent equation, which is y equals a times 1 minus r to the x or t. It's your choice. It's just a variable. And it's a minus because it's decay, because it's depreciating. So we're going to now fill in all of our values. So we get 800 times 1 minus 0.162 to the t. You can do 1 minus 0.162 if you want to and get a number. Again, somebody was asking about how we do that, and we have to go back to our old school decimals. 1 would be written as 1.000 so that we can line up all of our place values. And then we're going to take away from that 100 to get 99 to bring in a 10 to the thousandths place. So that's going to be 8, that's going to be 3, and that's going to be 8. So if you want, you could write it like this, but I'm not going to take off points if you leave it as that. But just know that on the multiple choice where you will have a calculator, you might see it either way. The next one says find the value of the cell phone after 3 years. So that tells us that t equals 3. So we just take our equation and put it to the third power. So we have 800 times 0.838 raised to the third power. So we're going to round to 2 decimals because it's money, and we are going to get that y equals $470.78. Then this comes into where we went in 5.4, so we've combined it into a single problem. It says find how old the cell phone will be when it has a depreciated value of $350. So in this one, where we have this as our starting equation, we're looking for t now. Change this to y equals 300, like that. So this is a calculator problem. So this is the graphing calculator that we learned the other day. So you're going to go into your graphing calculator, and you are going to type in these equations. So the first one, 800.838 raised to the x, and again the x is next to the green button. And then you go into y2, and you're going to type in that $300. Was that what it was? I can't see it right. Oh, 350. So you're going to type in 350, and then you're going to hit the graph button. And of course, right now it's not going to show it because our window isn't appropriate. So we're going to go into window, and we learned to change our x minimum to -1. And then our x max, we're trying to predict how long it's going to take it. So I'm going to leave it at 10. It might be more, but I'll be able to go back and change my window. Our x-min and our y-min, it's just easier to make them both -1 because we're looking at mostly positive data. And then the y max, whatever your second equation is, so in this case it's 350, you always want to make it more than that number. So I'm going to make it like 500 and then hit graph. So now we can see the point of intersection, and that these are intersecting some time between 4 and 6. So the way I find the exact value is I hit I'm going to pull up the calculate app under the graph. So I hit the blue button and then the trace button, and then I'm going to pick option 5 for intersect, and then it's enter, enter, enter. Intersection 4.667. It's hard to see on the screen there. So we're going to go to 3 decimal places, so it's going to be 4.677. So t equals 4.677 years old. Okay, last one in this column is going to be Suppose you want to buy a used car that costs $12,300. The expected depreciation of the car is 18.2% per year. Estimate the value of the car after 5 years. So same kind of problem. We have 12,300 is the starting amount. And then we're going to subtract after we convert this rate to a decimal. And then we are going to see the value of the car after 5 years. So we're just going to plug that into the graphing calculator, but we don't actually have to plug it in to the graphing part. We're just going to plug it in right here. 12,300 times 1 minus 0.182 raised to the 5th power, and we get $4,504.76 because we know how to round properly. Okay, we're gonna switch it to the next page. All right, write an expression to show the value of a rare postage stamp originally purchased for $5,000 that has been increasing in value by 11%. So R equals 0.11. Increasing means it's going to be a growth rate. So we're going to start with the initial amount. Who bought a postage stamp for $5,000? And then we're going to do 1 plus 0.11, and then it's going for 10 years. Okay, so we are going to just plug that into the calculator. So you can even take it to this one if you want. If this was the free response, we would probably just ask you to set up this equation right here, and that's where you would end. I mean, really, we are assessing whether you can do that, not how well you can punch into a calculator. But let's go ahead and pull that up. 5,000 times 1.11 raised to the 10th. And so if we really did ask for a number, that's going to be how much that postage stamp is worth right there. But I think the question just asks you to set up the situation. So let's see. Well, we'll just leave it like that. Okay, next one says the population of Whoville has been decreasing at a rate of 8.08% per year. Let's see. So we need to convert that. So you're going to have 0.008. Since Dr. Seuss passed away in 1991, if the population was 13,500 at the beginning of 2005, what expression gives it population at the beginning of 1998? Whoa. Okay, so let's see. We are going to see that it's decreasing. So y equals a times 1 minus r to the t. And then we know it started off at 13,500. And then we're going to do 1 minus 0.008 to the t. The only thing is that it's decreasing, and we said it started at 13,500, but we're going back in time. So what we're going to want to do is just make our t negative. So how many years is it from 1998 to 2005? It was 7. But since this number was the current number and we have to go backwards, we're going to make that a -7. So that's a little tricky just because of how we were using our initial value as the current value and we were going backwards in time. So that's why that t is -7. All right, the following exponential function represents the amount of bacteria in a petri dish. Identify if the function represents growth or decay, and then find the growth or decay rate. So this is from 5.3, and it's at the very beginning of 5.3, where we learn that e to the c either equals 1 plus r or 1 minus r, and you can figure out which one is growth or decay by looking at this right here. So because that value and that c value, which is negative 0.024, because that's negative, it's going to be decay. So if c is positive, it's growth, and if c is negative, it's decay. So we're going to take that whole thing and we're going to set it equal. So we have e to the negative 0.024 equals 1 minus r, since it's decay. Then we're going to subtract 1. Make sure you know how to combine like terms properly. And that equals negative r. And then we're going to divide by negative 1. And then we're going to plug, we end up with r equals e to the negative 0.024 minus 1 divided by negative 1. Just plug that whole thing into your calculator. So we're going to go second e to the negative 0.024 minus 1. Oop, make sure you get out of the exponent because that minus 1 is not. And then I'm going to divide it by negative 1. So I get 0.0237. And then we just need to convert that to 0.02371. And then we just need to convert it to a percentage. So we're now going to move this 2 to the right. So we get r equals 2.371%. Okay. Next one, the following exponential function represents the number of people that contracted a virus over time. Identify if it represents growth or decay, then find the growth or decay rate. So just like the last problem, we're going to go ahead and we're going to look at this value right here. And because that value is greater than 0, so it's positive, so we're looking at decay. So we're just going to hone in on that e to the 0.308, and we're going to do 1 plus r, and then we're going to solve for r, so we're going to subtract 1 from both sides, and we get r equals e to the 0.308 minus 1. So then from there, we're going to plug that into the calculator. The E button is right next to the number 4. You just have to hit second first. And that one was 0.308. And then we're going to get out of the exponent and hit minus 1. And we get 0.3. Do 5 decimals on these growth rate ones just because that will give us 3 numbers after the decimal place. So we get for this r equals 0.36070, and then we're just going to make that the growth rate as the growth percentage. So the growth rate percentage by moving it over 2. So then we get r equals 36.070%. Let me delete that r. It actually isn't the r part. Okay, last column here. Xavier deposited $1,200 into an account that pays interest compounded weekly. So if it says compounded, you're either using continuous or when it's compounded more than once per year. So our equation is P times 1 plus R over N to the NT. Okay, so we're going to make sure we get this information. 4.3% would be 0.043 as R. And we get Y equals initial amount, which is 1,200, times 1 plus 0.043 compounded weekly. N is always the number of times per year, and there's 52 weeks in a year. So we have 52 times t. And this one just says to write the function, so that's good right there. You don't have to plug anything in to the calculator. This one says Gabriel deposited $1,000 into an account that pays interest compounded biannually. So again, compounded biannually or semi-annually would mean that n equals 2, and then it's paying 6% interest, so r equals 0.06. So we're going to use the same equation as problem 8. So y equals 1,000 times 1 plus 0.06 over 2 times 2 to the t. But in this case, it does want us to find the amount, and our t value is 10. So we're going to do it like that. Now we're going to plug it into the calculator. So we get 1,000 times 1 plus 0.06 divided by 2. It was biannually, raised to 2 times 10. Hit enter, and you get $1,806.11. So we get y equals $1,800 or $1,806.11. Okay, next one, a principal amount of $600 and placed into an account compounded continuously. So that's our PERT equation. Anytime it says continuously, you will use this equation. So we know that our rate is going to be converted to a decimal. So then we get y equals, this is how long does it take to reach 1,000. So this is going to be another graphing calculator problem. So we have y equals 600e to the r, which is 0.035 t, and then we're seeing how long it takes to reach 1,000. So for this one right here, we're going to plug both of those into the graphing calculator. And then we're seeing how long it takes to get to 1,000. So when I hit graph, you can't see my graph because I don't have the right window. So my y max right now is 500, but I asked it to graph y equals 1,000, so I'm just going to pick 1,100. And then when I hit graph, I don't see my point of intersection in the graph. It's happening more to the right, which means I'm going to go change my y max. So I'm going to change that to like 20 and then hit graph. I have the point of intersection right here. So this calculator is a little different being on the iPad than your graphing calculator. So if it is on your graphing calculator, I'm going to say those directions just because that's what you'll have on the test. You're going to do second trace, hit intersect, and then just hit enter, enter, enter. I have to do a little bit more on my end. So just give me a second. And then the point of intersection is 14.595 years. So this is t equals 595 years. Okay, last little problem. Somebody bought a Muhammad Ali poster for $300 that compounded continuously. So that's the PERT equation. We see that the rate is going to be 0.167, and it just says write an exponential function to model the value of the poster. So that one, you're going to type in the initial price, which was 300, and then 0.167t. So that's the function, and then it's asking you to find the growth rate, which is like 6 and 7. So because we have an E in it, we can find the growth rate. And so the way we do that is because 1.67 is positive, we know this is a growth. So it's going to be 1 plus R. So e to the 0.167 equals 1 plus R. And then we're just going to subtract 1. And then we get R equals e to the 0.167 minus 1. And so then we plug that into the calculator and we get that R equals 0.18175. And then we're just going to convert that to a percentage to get the percentage growth rate. So it's going to be 18.175%.